Today we're starting section 9.6 in your textbook, which is counting principles. For the opening example, it says a new restaurant is opened and you offer lunch combos for $5. With the combo, you get one sandwich, one side, and one drink. The choices are below. So this problem obviously is a little bit dated with a $5 lunch, but it's still mathematically valid. So for the sandwiches, you can have chicken salad, turkey, grilled cheese. For the sides, chips, french fries, or fruit cup. And for drinks, get your choice of a soda or a water. When you guys first saw this problem back in grammar school or middle school, the way that you were probably taught how to do this was to draw a tree diagram. And that's how we're going to approach this for our first example. So, solving this thing with a tree diagram, first you're going to choose between chicken salad, turkey, or grilled cheese, and that's for your sandwich. And then, after each one of those possibilities, you get to pick chips, french fries, or a fruit cup, and that's a valid set of selections no matter what your sandwich is. And then, after each one of the, or whatever side you choose, then you get to pick your drink. Now the advantage of working with a tree diagram like this is, number one, it will tell you all the possible combinations in terms of how many there are. If you count up all those end branches, so to speak, you will end up with 18. So we know there's 18 combinations of meals that we could order. And the other thing it tells us, excuse me, is if we trace every path from left to right, it'll tell us every possible combination. So for example, a turkey sandwich with chips and a soda is one of the 18 possible total combinations. Our tree diagram is a good visual representation for counting problems. In addition to telling us how many possibilities there are for a given situation, it also tells us specifically what each possibility is. Unfortunately, tree diagrams can be difficult, if not impossible, to construct for larger problems. Also, for many counting problems, we do not necessarily care exactly what each individual combination is, just how many of them there are. So, when you're learning this for the first time in grammar school or middle school, this tree diagram, number one, will get the job done for the size of the problems, and number two, it's a very visual way to wrap your brain around what's happening. But once you get into upper level types of problems, it loses its efficiency. A more efficient way of determining the total number of possibilities is to use the fundamental counting principle, which is pretty universally abbreviated as FCP. Okay, one definition for this: in a sequence of n events in which the first event can occur in k1 ways, and the second event can occur in k2 ways, and the third event can occur in k3 ways, and so on, the total number of ways the sequence can occur is. So relating it back to the previous example, we have three events. The first event is choosing the sandwich. The second event is choosing the side. The third event is choosing the drink. So we have a K1, K2, K3. So we had three choices for the sandwich, three choices for the side, and two choices for the drink. That 3 times 3 times 2 gets us to the 18. So it's a significantly more efficient way of getting that number 18. The drawback is that we don't necessarily know, or we don't know what each of those individual combinations are. And for most problems that we do at this level, we really don't care. All right, some practice problems with this. Jeff is ordering a new car. He chooses the XT20 model. He must select from the following options: 5 exterior colors, 4 interior colors, manual or automatic transmission, 4-cylinder or 6-cylinder, 2-wheel drive or 4-wheel drive. How many versions of the XT20 could he select? So here we have 5 events. The first event is picking the exterior color. Second event is picking the interior color. Third event is the transmission. Fourth event is the engine. Fifth event is the 2-wheel versus 4-wheel drive. So how many options does he have for each one of these? Well, there's 5 exterior colors to pick from, 4 interior, 2 transmissions, 2 engine sizes, 2 drivetrains. So the fundamental counting principle says we multiply all that together and we get 160 possible cars that he could select. Number 2. A pizza shop runs a special where you can buy a large pizza with 1 cheese, 1 vegetable, and 1 meat for $9. You have a choice of 7 cheeses, 11 vegetables, and 6 meats. Additionally, you have a choice of 3 crusts and 2 sauces. How many different variations of the pizza special are possible? So this one has 5 events. First one is picking the cheese. The second one is the vegetable. Third one is the meat, the crust, then the sauce. How many options are available at each one of those events? 7 cheeses, 11 vegetables, 6 meats, 3 crusts, 2 sauces. Fundamental counting principle says we multiply all that together. We get 2,772 possible pizzas that could be ordered. All right, as a side note to this problem, 11 vegetables. Most people would have a hard time coming up with 11 vegetables, let alone 11 vegetables that you'd possibly want to put on a pizza. Just a side note. Anyway, back to the next problem. Right, how many ways can the symbols, and we have 5 different Greek letters, can be arranged? So we're making 5 choices, or we have 5 events. Which symbol do we put first? Which do we put second? Which do we put third? Etc., etc. So there are 5 total symbols, so there are 5 to pick from for which one we want to put first. After we choose whatever one goes first, there are 4 left to pick from for which one goes second. Then after the first 2 are chosen, there are 3 left, and then 2, and then 1. Shorthand for this is 5 factorial, or 120 total ways that those symbols could be arranged. All right, number 4. In order to make operations easier, a company wants to identify each of its employees using an ID number. The president decides he will use 1 letter followed by 2 digits. If the company has 1,600 employees, will there be enough numbers for each person to be assigned 1? Support your answer. So we have 3 events, so we're making 3 choices. It's a letter followed by 2 digits. So 26 letters to choose from for the first slot of the ID number, and then 10 digits for each of the next 2. 10 total digits because you have 1 through 9, and then the digit 0 is the 10th one that some people forget about. So 26 times 10 times 10 is 2,600. So yes, there will be enough IDs for every employee to have 1, because the 2,600 IDs is more than the 1,600 employees that this company has. All right, a classic type of problem that's in every book that deals with this as a topic is a license plate problem. A state issues license plates consisting of 3 letters followed by 2 digits. The letter O is omitted because it looks too much like the number 0. How many cars can the state register if letters and digits may be repeated? Now, in some problems, it is inherent to the problem that something should or shouldn't be repeated. sometimes it's not necessarily obvious. Sometimes they state what's obvious. So it could go a lot of different directions here. Normally, you wouldn't think there'd be anything against repeating letters or numbers on a license plate, so you wouldn't inherently, due to the nature of the problem, think that you can't repeat, but in this case they're emphasizing that you can repeat. So we have 5 choices we have to make. The first 3 slots are going to be letters. The second 2 slots are going to be digits. Now their grand total of 26 letters, but they specifically said O is omitted. So 25 times 25 times 25 for the first 3 slots. Now it said O is omitted. It didn't say anything about omitting 0. So all 10 digits are fair game for the last 2 slots. Okay, part B of this same question. How many cars can the state register if letters and digits may not be repeated? Now that's something we would never assume. That's specifically like made up just for the purposes of this problem. So how would that play out in terms of what we do? So we still have that omitting O as a restriction from the original prompt here. So the 25 letters that are allowed for the first slot are fair game. And then whatever we choose here can't go there. Whatever 2 are there can't go in the third slot. So for the letters, we have 25 times 24 times 23. And then once we hit the 4th selection, all 10 digits are fair game. We can't repeat digits, so there are 9 left for the last slot there. All right, number 6, determine how many ways a president, vice president, and treasurer could be chosen from a math club comprised of 7 members. So we have 3 events. You're choosing a president, you're choosing a vice president, and you're choosing a treasurer. Now it doesn't specifically say that you can't repeat, but in an election process it's assumed that once you hold an office you can't hold another office. You can't be president and vice president both at the same time. Imagine the world anarchy that would occur if you allowed somebody to be president and vice president of a math club of 7 members. Where would it end? Anyway, back to the problem. 7 ways to pick the president. Who's ever president can't be vice president. 6 people left to choose from. Who's ever president, vice president can't be treasurer. That leaves 5. Fundamental counting principle, multiply those together. Number 7, a multiple choice test has 10 questions with 4 answer choices for each question. How many different ways could you complete the test? So we have 10 events here. Each question that we answer is an event. It's multiple choice with 4 options at each. So there's 4 ways to answer the first question, 4 ways to answer the second question, etc., for a grand total of 4 to the 10th, or 1,048,576 different ways that the test could be answered. Okay, putting that in the context of probability, which will be our next section, if you were to take a 10-question multiple choice test with 4 options at each, and you randomly guess, your chances are worse than 1 in a million of getting 100 on that particular assessment. And number 8, if there are 11 people on a baseball team, determining how many different ways a pitcher and catcher could be chosen. So this has that implied you can't be the pitcher and the catcher both at the same time, unless you're a Bugs Bunny cartoon. Perhaps that's a little bit dated for some of you, but maybe you've seen that one. 11 ways to pick who the pitcher is going to be. Whoever the pitcher is can't be the catcher at the same time. 10 ways to pick the catcher. All right, sticking with the baseball theme. A baseball coach is determining the batting order for the team. The team has 9 members, but the coach does not want the pitcher to be one of the first 4 to bat. How many batting orders are possible? So when we start making a lineup, the pitcher can't be one of the first 4. So there are 8 people to bat first, and then 7, and then 6, and then 5 to fill in the first 4 slots. Okay, after that, all remaining people are fair game. So now it's going to be the 5 remaining times 4 times 3 times 2 times 1, or after you multiply that together, 201,600 different batting orders are possible. All right, last couple questions for this part of our counting principles. How many 4-digit numbers can be formed under the following conditions? The leading digit cannot be 0, and the number must be less than 5,000. The number less than 5,000 refers to the entire big number that gets formed from the 4 digits. So we have 4 events, and we're making 4 choices. Now the leading digit can't be 0, and the number must be less than 5,000. So that means it has to start with either a 1, 2, 3, or 4. Or in other words, there are 4 options of what could be first. Other than that, all digits are fair game for the remaining 3 slots. Okay, part B. The leading digit cannot be 0, and the number must be even. So the leading digit not being 0 means there's 9 things that could be in the first slot. If the entire number must be even, that means it has to end in a 0, 2, 4, 6, or 8, which means there's 5 things that could be at the end here. Given the restrictions we have to deal with, any of the 10 digits are fair game for the 2 middle slots, so we have 4,500 numbers that could be formed given those conditions.